All right, here we go. We are on the last lecture for fuel metering devices. We're going to talk a little bit about fuel system maintenance. Now, just a couple things just to point out. This is not going to be a comprehensive dive in how to maintain everything on a fuel system. This is just kind of a couple general overview points about good maintenance practices and kind of what we're looking at within those systems. We're going to be a little bit heavy on reciprocating engines because there's a little more to do, and we'll talk a little bit about turbine fuel metering systems as well. So, starting off with our fuel system for a reciprocating engine aircraft. As we talked about before, our cutoff point for the fuel system when we're talking engine versus airframe is typically going to be wherever our engine driven pump is, or the strainer that goes into the engine driven pump. Overall, when we talk about inspecting a fuel system, at least for me, I tend to prefer to go top down. When I say top down, that doesn't necessarily mean the physical top of the aircraft. I'm talking about logical top. So that means when I start my inspection, I'm going to start in the fuel tank, right? So we go tank first, right? Number one. And then we're going to move on. We're going to take a look at the subsystems within that tank. So we're looking at things like drains, we're looking at fuel quantity senders, we're looking at the connections to the tank, we're looking at breather lines, we're looking at vent lines, all the different things that are up in the tank. After that, we're going to start looking at, number two, our lines that connect to the engine portion of the fuel system. So all of the tank outlets, that's going to include our selector valve, making sure the selector is functional. Again, a nice thing with reciprocating engine fuels is because we have all this blue dye in 100 low lead, it makes it really, really easy to see where there has been a leak because you're going to see a lot of blue staining around an area where a leak has been. So we're going to take a look at our fuel selector, the lines going to the fuel selector, the lines going from the fuel selector. In some cases, we may have fuel filters that are incorporated or combined with the fuel selectors. So we want to make sure we take a good look at that. We're going to run through all of our tank and low point drains along the way. Once we get to that point in time, if we are so equipped, we'll take a look at our gascolator or other type of fuel filter on the engine side of things. And then we're going to take a look at our engine-driven pump, if so equipped. Remember, a lot of gravity-fed aircraft fuel systems may not have an engine-driven pump, but if we have it, we're going to inspect our engine-driven pump. Again, looking for leaks, anything that would indicate that it's not operating properly, looking for any leaks through the weep holes. It would indicate that a bearing is starting to go bad and we're leaking fuel, bypassing it towards the engine. We'd also want to make sure that as a part of our run-up on the engine, we observe that we're actually getting the correct fuel pressure from the pump. So if we have a fuel pressure indication gauge in the cockpit and we have control, we can switch off a boost pump while the engine is running and make sure that we maintain the correct PSI throughout the range of operation off of the engine-driven pump to make sure that our relief valve is adjusted properly. Past that, we're going to take a look at the lines that connect to the fuel metering device, whether it's a carburetor, fuel injector unit, you name it. We want to make sure those lines look good and everything is clear. After that, we're going to get to our fuel metering device. And as a part of that, we're going to take a look at adjustments. We're going to take a look at rigging. We're going to take a look at filters. A lot of these fuel metering devices are going to be equipped with a last chance filter or a finger screen or something like that at the fuel inlet to try to protect the device from anything going on. And once we get past that, we're going to take a look at the distribution system. So in this case, whether it happens to be primer lines, happens to be injection lines, a flow divider, and a spider for a primer, our injectors, you name it, we're going to take a look at distribution. Or if it happens to be just carbureted, we'll take a look at our intake manifold and all of the connecting points to make sure that we see no evidence of fuel leaking there or obvious leaks through the system. It's pretty straightforward, pretty easy. So that's the checklist that I like to use as I go through one of my inspections. We're going to talk a little bit here is about specific adjustments on carburetors and fuel injector units. So let's start with the carburetor. So let's picture that you walk up to an aircraft, you install a new carburetor, or you happen to have an issue with the carburetor and we need to replace it. We need to figure out how to do two primary things. There's two very, very important things we need to figure out. That is our idle RPM adjustment and our idle mixture adjustment. If either of these are not accurate, then we can have some serious issues. If the idle RPM is not set properly, then it's going to cause issues for the engine running smoothly when it's on the ground. It can give us a bad baseline for things. If our idle mixture adjustment is not correct, you may think, well, it's just idle. It's not that big of a problem. But here's the issue. If we go way too rich on our idle mix, so if we're at rich or above, then the majority, and I'm going to say the vast majority of issues with plug fouling is going to come from having an excessively rich mixture in the idle circuit. So as the aircraft is running at low RPM, we're scheduling way too much fuel into the idle circuit, and it's just loading up carbon and unburnt fuel and lead onto the spark plugs, and then we start getting spark plug issues or ignition issues, which we can spend a lot of time troubleshooting if we don't know what we're looking at. So making sure our idle mix is adjusted properly helps an awful lot with plug fouling and making sure that it runs properly. On the other side of things, if we are way too lean, then we can have an issue with acceleration. And again, you say, well, what does idle mix have to do with acceleration? Well, part of that is the carburetor is sitting in its idle circuit when it's at idle speeds, up to a certain threshold. Once we move beyond that threshold, we're going to shut off or otherwise close off the idle mixture adjustment, or it's not going to be a factor for how the engine operates. But the problem is, if there's a big gap, right, between our mixture setting at idle and where we need to be in for the power band to come in, then what we wind up with is this kind of weird hesitation in between, right? If you hit it really hard and the accelerator pump pushes fuel out, then it may mask it. But if we do a nice smooth acceleration all the way to full throttle, what you might notice if you're set too lean is that this first initial setting, as we come off of the idle stop, is going to go and it's going to try to catch up because we don't have enough mixture at idle to be able to support that transition into the regular fuel metering circuit. So that's something pretty important as well. So a couple of rules as we try to set our idle mixture adjustment. My process that I prefer to do is try to set my idle RPM first. Now, this can take a little bit of fine tuning once you adjust your idle mixture because the idle mixture can have an impact on how quickly the engine turns at idle if the mixture is really, really off. Typically, one coming off the bench or something like that is not going to be that far off, but it could be, so it may require an additional check. But effectively, whatever we end up doing for these adjustments, we want to make sure that the engine is up to normal cylinder head and oil temperatures. We have to give the engine a good long run up to make sure that it's heat soaked and it's in its normal operating range. Once it is, we can pull the throttle all the way back until we contact this idle stop here, and we're going to observe our RPM. If our RPM is perfect, great, we're done. We don't have to worry about it. If the RPM is too high, then what that means is our throttle plate inside here needs to close further. So we need a little more travel on this throttle control arm to be able to bring the idle RPM down. What that means is we take this screw right here and we back it out a little bit so that this idle stop can move just a little bit further. Back it out a little bit, and then what we want to do is accelerate the engine just a little bit. It doesn't have to be full throttle. Take it up to 1,000 RPM or something like that, and let the engine clear out a little bit, and then we bring it back to idle and observe the idle RPM that it sets on. If we need to make a slightly further adjustment, then we can do that, but if it's fine, then nice. On the other hand, if idle RPM is way too low, we're going to know pretty quick because the engine is going to struggle to run. It's going to cough and sputter. It's going to sound pretty uneven because we do need a minimum speed for these engines to run smoothly. If we need a higher idle RPM, then we're going to do the opposite of what we just talked about. We're going to take this screw and we're going to drive it clockwise into the idle stop here. And what that's going to do is it's going to force this idle stop out, which opens the throttle just a little bit more. That allows a little more air to flow through at idle, and that gives us a better, higher idle speed. Again, it just depends on what situation that you run into. Once my idle RPM is set, now I can take a look at my idle mixture. And that's controlled by our idle mixture screw right here that goes directly into the idle circuit. Now, all we're changing is how much air we allow to bypass into the system. So typically as we allow more air in, it's going to provide a leaner idle mix. As we close air off, it's going to provide a richer idle mix. So keep that in mind as we take a look. So if we find that our idle mixture is off, we're going to note that through what the engine's behavior is as we try to shut it down. Now, there's two ways to do this. We can either shut it down each time and watch, or if you're quick on the mixture lever, what you can do is pull the mixture lever back further and further and further all the way to idle cutoff. Now what you're going to watch is on the RPM gauge on your tachometer, you're going to be looking for a slight increase in RPM. So if we're talking most carbureted systems, you're looking anywhere between like 10 to maybe 30 or 50 RPM increase when we shut down the engine. And the reason for that being is, remember, we have this stoichiometric value. If you can picture our power output graph that we had, talking about lean of peak. So as we increase our idle mix, we drew a pretty simple graph here. We'll have our mixture going this way, and we'll have or that'll be our power, and we'll have our mixture going rich and lean in this direction. So when we're lean, we're going to have a lack of power. As we increase the mixture, we're going to get more and more power all the way up to our stoichiometric value right there. And then as we go further rich from that, we're going to start to taper off in the amount of power that we produce. So what happens when you pull a carburetor to its idle cutoff position at idle is we're normally living a bit rich of stoichiometric. So what happens is as the fuel mixture starts to lean out, once we cut it off, we actually briefly pass through our stoichiometric value, which produces more power, right? Pretty straightforward, and then our power dies off. So when we pull that, we're looking for that slight increase in RPM, because what that's going to show is that we are running just rich of stoichiometric. We pass through and we get a little bit, and then we die off. If we get a huge jump in RPM, it means we were way too rich. And so there's a big difference between where our idle setting was and where that stoichiometric value was. Conversely, if we pull the mixture and we don't see a rise at all, that tells us we were either right at stoichiometric or we were on the lean side of the curve, and so it just died off. It didn't go through that extra amount of power before it died. So again, if you're quick on the mixture lever, you can pull that all the way back, watch that rise start, and before the engine dies, you can push the mixture in back full rich and catch the engine before it dies. That way you can make adjustments back and forth as you're working on the aircraft. On the other hand, if it's not particularly accessible or it's dangerous to try to get at while the engine is running, then we can just shut the engine off completely, make a couple adjustments to the screw, come back and try it again. One thing I recommend is when you are making adjustments to either the idle mixture screw or the idle RPM screw, is make sure that you are counting, right? Counting the number of turns you do. So I like to go in half turns. It makes it a little bit easier to track because usually there's a flat on the end of the screw. If I was going to draw it for you, we have the screw right here, and typically you're just going to have a spot for a flat head, just like so. So as I rotate it, I can turn it 180 degrees and say, hey, that's one half turn. If I turn another 180 degrees, I know that's one full turn. It just makes it a little bit easier to track what's going on. But that's your basics. I like to go idle RPM first and then idle mixture. As I mentioned before, if your idle mixture is really, really far off, then it may actually affect your idle RPM. So if you get your idle mixture finally dialed in, double check to see that your idle RPM is set good. Otherwise, you may have to take a couple more adjustments, but that should be it. As we take a look over here at the fuel injector side of the world, we're going to have fundamentally the same thing, but a different way of doing it. Our idle speed adjustment is right here. It's going to be familiar to what we saw on the carbureted version. We just have a screw that goes in and out that changes the position of the throttle when we're at idle. So again, if we need a little more RPM, then we can screw this in a little bit, and it's going to open up the throttle plate more at idle, or we can back it out and it's going to close it a little bit more, and we get the right thing. Similarly, with our idle mixture, instead of having a knob that goes in and out to be able to block off or open up a passage, we have this idle mix adjustment leakage that goes to our idle valve, which is inside the fuel metering portion of our throttle body. So what we need to do is we're either going to lengthen or shorten this linkage by turning the idle mixture adjustment. So Again, typically it's going to extend a little bit to enrich in and shorten to lean out the mixture. And we just see what we get on shutdown. Again, we should be looking for, with a fuel injected system, somewhere between like let's say 15 to 50 RPM maybe. And part of that is just due to the fact that the system's a little bit more efficient, but that's kind of what we're looking at. It should be the range that we're in. So that's the basics for setting those with carburetors or fuel injectors. The TCM system is a little bit different, but it still uses a linkage. If you want to see it in closer detail, let me know and I'll show you on one of the aircraft we have in the hangar. I just couldn't find a great picture of it that I liked, so it's a little bit easier to describe in person. Last thing we're going to talk about are turbine fuel metering systems and how we maintain those. As mentioned before, my procedures for inspection are going to be pretty similar. But one thing that we're looking at with turbine engine systems is most of them are not really adjustable out in the field. In most situations, if you have a real issue with a fuel control system, then you're going to be removing it and sending it out. And when we talk about, say, our EEC, so the electronic fuel control systems, or we talk about FADEX, either one, we're going to basically remove and replace. The changes and how it operates are going to come either from a different unit or from a software update or anything like that. So you're almost talking a little more of an avionics side of the world, where what you're going to be looking at are like bite tests to check the internal circuitry or to check the software. It's all going to be computer based effectively. The one exception to this is if we have a true hydromechanical fuel control unit, which really there are very few out there anymore. But the process that we talk about with a hydromechanical turbine fuel control is what we call a trim or engine trimming. And the whole point of engine trimming is we're going to set the maximum power output and try to calibrate the fuel control for that. And what we're using is typically either going to be one of two things. We're going to be looking at EPR, so our engine pressure ratio, good old EPR, or we're going to be looking at turbine outlet pressure, which takes longer to write than say, go figure. So either EPR or turbine outlet pressure. And the whole point of that is we're trying to see how much pressure the engine is delivering. So there's a specific power output, not dissimilar from like the static horsepower check that we'd have on a reciprocating engine. We should be able to achieve a certain RPM at full throttle. The same concept is similar with a turbine engine. If we are at full power, we should have a certain amount of pressure ratio, or we should have a certain turbine outlet pressure if everything's calibrated properly. There could be a couple of things. If we start to have wear and tear on our compressor blades or things like that, it could also negatively impact our pressure ratio or the outlet pressure. It just kind of depends. So what you need is a nice calm day. And ideally what you want to do is face the aircraft into the wind, but if there's little to no wind, that's preferable because we don't want to throw off the pressure ratio going in and out of the engine, which having a strong headwind could do. Temperature can also play a factor in, so we want to get an idea of what the true temperature is going into the inlet of the engine. That way we can adjust for any changes in density due to air temperature as we're doing the trim. But otherwise, the engine is rolled up to full throttle and it's going to be allowed to stabilize for, say, 5 minutes or so. And once it's stabilized, then the readings are made on either the EPR over here or the turbine outlet pressure and compared with what the ratings for the engine should be. And then some adjustments can be made to the fuel control device if need be. But that's the basics behind what we see with the fuel trim. Again, it is extremely, extremely rare in terms of what you'll likely see, especially moving forward, because most of what's out in the world now is either going to be controlled by an electronic device, EEC, or it's going to be a full FADEC. That's going to be a different procedure. So that's the basics. Hopefully this has been informative. I look forward to seeing you out in the lab, and we'll tackle a little bit more on fuel metering devices.